Apologies for starting class a tad late, but I promise to not try and keep you 5 minutes late as a result. We should be able to still get done on time. Still working on catching up with homeworks. 7, 8.1, and 8.2 are being graded. The solutions are posted for those, though. Everything else, though, is graded. 8.3 was due today. Hopefully that one was a pretty straightforward one, the one with the fixed supports. Okay. 8.4 is assigned today. I do want to be clear, 8.4 is assigned today, due Monday, but 8.5 is not going to be due till after break. And my reason for that is you all have a project to do. So I'm going to give you some breathing room. Now, if you are making headway on the project and you can go ahead and knock it out, go ahead and knock it out. But I'm not going to make it due until after break so that you don't have a bunch of stuff all due at once. The only other thing I wanted to mention is that if you are free today at 1 p.m. At 11:01, we have a candidate for our transportation engineering faculty position who's making a presentation today. And so you're more than welcome. Sound good? All right. Okay. So today what we're going to do is we kind of touched on this last time, but I really want to dig into the idea of applying all this influence line stuff. For the past few lectures, we've been learning how to construct influence lines, but we've just barely started to discuss the idea of actually using them, okay? Help if I turn that on. And it would help if I plugged it in. Man, I'm not firing on all cylinders today. There we go. Okay, so let's just make sure we're on the same page. We are still, talking about the Mueller-Breslau principle, so we are still using the same concepts. Although today we're actually not really going to be drawing very many influence lines because the influence lines are already going to be drawn for us because we're going to be using an example we've already done. I do want to make sure, though, that you do understand the patterns for influence line for reactions and that you do understand the patterns for influence lines for shearing moment. Okay. Now, we talked about this last time, but I kind of want to just make sure that we're all clear on this. The way I see it, there are two primary applications for influence lines. The second application is really what influence lines were developed for in the first place, which is to determine worst case scenario loadings. But that really wouldn't make them all that useful unless you could just use them to perform the actual structural analysis itself. So to begin, the first application for influence lines is to just do the structural analysis. Okay, direct structural analysis. You can replace equations of equilibrium with an influence line if you're solving for responses at a given point. Okay, so the idea is that if we know the response due to a unit load, can't we understand the response due to any load? If I have a simply supported beam, okay, and I put a load of, let's say, 1 kip right in the middle, what are the reactions? They're a half, right? And a half. Well, the question then becomes, what if I change that 1 kip? What if I change its magnitude to, 70 kips? What are the two reactions? They're 35 apiece. And how did you get 35? You basically, before now, you would have said, well, how did I get 35? Well, I just took 70 and divided it by 2, okay? I want you to think about it a little differently now. Instead, I propose what you were doing without really thinking about it is you took the magnitude of the load and you multiplied it by whatever the value of the influence line was where the load was applied. Does that make sense? That is the first application. That is the first application of an influence line, is to just do the structural analysis. Okay? And so in general, the idea is that if you have an influence line constructed for a given response, you can compute that response for really any load anywhere by taking the values of the loads, the concentrated loads, times the values of the influence lines, and taking the distributed loads and multiplying them by the associated areas of the influence lines. Now, one thing I'll say about this is that there is a slight caveat that this only works, or I should say only works easily, for loads that are vertical, right? if you have loads that are inclined or loads that are horizontal or something like that, it does make the application of influence lines a little trickier. It also would be trickier to apply an influence line if we were dealing with a triangular load or something like that. It's not to say you couldn't theoretically do it, because you can. It just makes it a little bit more interesting. But I would argue that we never really need to do that in practice. You'll understand that a little better on Monday, but long story short, whenever we're looking at real-world loads that we're applying to, let's say, bridges, we're never really applying moving triangular loads on bridges. It doesn't really work like that. Really, the only loads that we're applying that move on bridges are point loads and distributed loads. So for that purpose, influence lines are going to work just fine. And we did an example last time where, let me escape this just to kind of bring that example back up. We did an example last time where we said, okay, I have a beam with just a bunch of loads on it. Let's compute the reaction at D. And the first way of doing it was just the way that we did it the very first week of the semester. Just some moments a day to solve for a reaction at D. And that'll work. There's nothing wrong with that, okay? But another way is to directly use the influence line. And so what I did is I drew the influence line for the reaction at D, and this is what it looks like. And so if you notice the way the beam is structured, I've got these divisions at every quarter point. So I identified the quarter point indices on the influence line. And then what I said is, okay, let's take the load times the values of the influence line, the point loads times the values of the influence lines, and let's take the distributed load multiplied by the area under the influence line. And I come up with this expression, and by golly gosh, we get the same reactions, okay? So this is honestly, like when I first saw this, blew my mind that you could do that. That you could just draw an influence line and load times value and distributed load times area and just get the answer. It was just crazy. But I think it's a really sort of an awesome serendipitous finding in the area of structural analysis. But I think what we need to talk about today is the real star of the show. What is the real point of an influence line? And the real point is worst case response, okay? And so what do I mean by that? I want to go back to this discussion of loads that move, okay? So if I have a bridge, let's say here's my bridge, and I have a load that moves. That load could be a single vehicle, or it could be a stream of traffic, or both. It doesn't really matter, okay? Where do I put that load to generate the worst case response, okay? I mean, as analysts, we need to know where to do that, and we need to know that response for one very simple reason. We need to be able to design, okay? If you're designing a bridge, okay, let's give you the bare basics of design. Whenever you're designing, there are two sides of the equation. There's the loads and there's the resistances. The loads are what we're talking about in this course, which is, all the structural analysis, all the shear diagrams, the moment diagrams necessary in order to determine what is the loads that we need to design for. And the resistance is how strong the element actually is. And as long as the resistances are greater than or equal to the loads, the beam is safe, or the structure is safe. That's structural analysis or structural engineering in a nutshell. Okay? So if we have a structure that is subjected to loads that move, we need to know the worst case loads to design for. Okay? Well, that's where influence lines come into play. Okay? So if we have concentrated loads, I propose that we place those loads wherever the highest value is on the influence line. And if we have distributed loads, we just place those everywhere that we need in order to generate a maximum response. And what that's going to generate is what's called an envelope of results. Okay? And an envelope, I've mentioned this term before, but an envelope is just a range of possibilities for a given loading at a particular point. And instead of making this super esoteric, let me give you a visceral example. Okay. So here's a beam. Okay? Here's a beam, and I have here the influence line drawn for the shear right there. Okay? Now, would everybody stipulate that this is pretty much what the influence line is going to look like? Equal slopes, a total jump of 1, negative 1/3, and 2/3, right? Everybody with me on that? Okay. Now, the influence line, if we look at the areas, the influence line has a region of positive area, and it has a region of negative area. Make sense? So as a result, here's what I propose, okay? If I had a distributed load, let's say it's 2 kips per foot, and I have the freedom to put that load wherever I want, where should I put that load in order to generate the worst case scenario? And really more specifically, what I should say is the worst case scenarios, okay? Let me kind of show you what I'm talking about. All right, so here's my beam. I propose that there are 2 scenarios. The first scenario is this, okay? So if I had a 2 kip per foot load, I propose that one of the worst case scenarios is to place it here, okay? Why am I placing it here? Because this is where my influence line tells me is where all the positive area is, okay? I propose that you cannot develop a load placement that will generate a larger positive response. You can't do it, okay? Because that's what the influence line says. The influence line tells you what is the response at that section due to the load, the moving load moving everywhere across the beam. This is the only place that you can get a worst case positive response. And how do we actually compute that shear? We take the load times this area, base times height over 2, okay? And when you chunk that out, you get 26.67 kips, okay? So this, I propose that you cannot generate, if we're talking about this point on a beam and a 2 kip per foot load, there is nobody in here that could put the load on the beam that will generate a bigger value than that. Can't happen, okay? Now, on the flip side, where should I put the load if I want to generate the worst case negative shear? I ask you. If this is the load placement for the worst case positive shear, where would be the worst case placement for the largest negative shear? Everywhere else, right? So everywhere else would be that, okay? All right, and what I have here is the same idea, load times area, okay? So here's what that looks like, okay? So if I were to plot this, right? So X and, I don't know, we'll call this shear over here, right? So we'll call this X equals 0, we'll call this, you know, X equals 10, X equals 20, you know, 30, 40, 50, 60, X equals 60, right? So why am I going from X equals 0 to X equals 60? Because the beam is 60 foot long, right? And I propose that at X equals 20, we have a positive shear of 26.67 and a negative shear of negative 6.67, right? Are you with me on that? This range right here is my envelope. And what I'm saying is, for that load, there is, if I have a 2 kip per foot load and I'm considering that point, there is no way that my shears can be outside this range. No way, okay? So this tells me the range of shears I need to design for. So if I pick a beam, for example, that has a shear capacity that can withstand these 2 loads, it's safe. Does that make sense? Everybody okay with that idea? And so what we do in bridge engineering is I picked a point 20 feet from the left support. Well, that'll work for that point, but how many points do I need to pick? And this is where I said common practice is to do this analysis at 10th points along the bridge. So, and we'll talk about that a little more on Monday. Okay. Now, what I want to do now is I'm going to complicate the situation a little bit because I need to, again, introduce a little bit of reality. I want to introduce some terminology, and that terminology is dead loads and live loads. How many of you have heard the term dead loads and live loads? How many of you have heard that? All right. Can anybody give me an actual definition of what dead and live loads are? What are dead loads?
Points that aren't moving.
What's that?
Are they points that aren't like loads that aren't moving? They're just static?
That's pretty much exactly right. Dead loads don't move. Live loads do, right? That's the difference, right? Okay, but that is 100% sure, 100% right. Okay, so what are dead loads? Dead loads are permanent loads that remain stationary. Okay, so one of the most common dead loads that we must design for or account for is a structure's own self-weight, okay? The structure's own self-weight. The thing about the structure's own self-weight is it's applied everywhere, okay? The dead loads, if we're talking about self-weight, are applied everywhere. Live loads are transient. Live loads move, and they are moved to generate the worst case response. So if dead loads are applied everywhere, live loads are applied anywhere, okay? Those aren't the same thing. We move live loads in order to generate the worst case response. And an example of that would be traffic on a bridge. We can put traffic on the bridge anywhere, right? And so like this example here, the 2 kip per foot load, when I'm the analyst, I'm going to consider the situation of the traffic over here, and then I'm going to consider the situation of the traffic over here and develop a range, okay? So we need a differentiation. Dead loads are not going to generate an envelope. Dead loads are just going to give you a value. Live loads, however, are going to give you a range. So if we're analyzing a beam, what we're going to be interested in finding is, let's say, a dead load shear, but also for live load shears, we're going to have a live load positive and a live load negative. Does that make sense? And then for moments, it's the same thing. We're just going to have a dead load moment. We're not going to have a range because the dead loads aren't going to move. But the live loads are. Does that make sense? Is that everybody good? Okay. Let's look into that. So, I got a little bit of an interesting example. So, we're going to go back to influence line 2, okay? Let me scroll this over. There we go. Come on. Okay, we're going to go to influence line 2. All right, so, or what do I mean by influence line 2? This was the second problem that we did, okay? And just to make sure that we're all clear on the scope, okay, we have this section of interest. So we're interested in this section right here. So if we want to apply a real world scenario, let's say that there's a connection right here on this beam, and we really want to understand what the shears and moments are at that point, okay? So we draw an influence line, okay? We draw an influence line for the shear and the moment at that point. And by golly gosh gee, we've already done that, okay? We did that a couple lectures ago, okay? So if you want, I'll give you a minute. You can copy these down if you don't already have them. These are the influence lines for the shears and moments at that section, and we already derived that in a previous example. So I'll give you a minute. Do you need a minute, or everybody good? I think everybody's good. Okay. So what we're going to do is we're going to calculate the shear and moment due to a dead load of 1.2 kips per foot, and then the shear and moment envelopes due to live loads of, and then I give you a distributed kip per foot live load, and then a concentrated 25 kip live load. Okay, so I've given you a lot here. Okay, so ultimately what we're trying to do is we're trying to calculate these 6 values. This is what we're trying to figure out. Okay. We're trying to figure these 6 out. Now, in order to do this, before we start using the influence lines, the first thing I think we ought to do is we ought to get our areas, okay? So let's start off with the shear influence line. Let's make sure everybody's awake on this rainy Friday late morning. What we need to do is we need to compute the area under the curve, okay? So I'm going to start, I'll do this one right here. So we need to compute the area under this triangle. So it's 0.3 times 6 over 2. So 0.3 times 6 over 2 is 0.3 times 3, or it is 0.9. Is that okay? Now this one right here, let's see, it is 0.7 times 14 over 2. 0.7 times 14 over 2 is 0.7 times 7. That is 4.9, but it is negative 4.9. Is that okay? Okay, and can somebody help me with this? What is the height times this entire base over 2? I'll make y'all do some work this morning. 4. Right? You could do each region separately, but really what's going on is this entire area is positive 4. Okay? Is everybody okay with that? So here's what I want to show you. For section 1-1, oh, sorry, mouse. The positive area is 4.9. The negative area is negative 4.9. I don't know why my pen's, it's like it's running out of ink right there. I don't know why. Does that make sense? This is the total amount of positive area. This is the total amount of negative area. So far, so good? Okay, let's do the same thing for the moments. All right, so this one right here, 4.2 times 20 over 2, I think that's 42. Positive. I think this one is negative 24. Y'all see how I'm doing that? Just the entire base times the entire height over 2. You can do them in separate right triangles if you want, but that'll work too. Okay. Now let's make sure we remember what the beam looks like. Here's what the beam looks like. Let me draw it up here. And then we've got a hinge right here. Okay. Now, so let's handle these loads one at a time. So the first load is a dead load, and it is a dead load of 1.2 kips per foot. Where do we apply that? Everywhere. That's exactly right. It's a dead load. It's not moving. And so we're going to assume, unless otherwise noted, that this is a distributed load to be applied everywhere. So this is our dead load. And what we're interested in is the shear right here due to that load. Now, before we had influence lines, what I would tell you to do is compute reactions, draw a shear diagram, look at the shear diagram. We don't need to do that. We have an influence line. How do I find the shear and the moment right here due to that load? How do I do that? Use the influence line, right? So, here's what I propose. If I want to find the dead load shear, I take 1.2 kips per foot and I multiply it by what? What do I multiply it by? And what area? Exactly. All the areas, right? It'd be 0, right? Because what we have is a 4.9 minus 4.9. The dead load shear is 0. So if you were to actually draw the shear diagram for the dead load and look at the shear right there, it would be 0. And if you don't believe me, compute the reactions. Put it in masstand. Analyze it. You'll see it's 0. Now how about the dead load moment? We would take 1.2 kips per foot and we would take all of the areas. Now, if you're hyper concerned about units, these units are in feet and these units are in foot squared. So that's why it comes out in foot kips. What is our dead load moment going to be for this? 21.6 foot kips. Do I have a second on that? Because everybody brought their Casio FX115ES Plus or similar scientific calculator to class, and everybody's sitting here looking at their table like, Dr. Mike's not going to call on me directly and make me get out my calculator from my backpack. He's not going to do that. He's not going to go to Mr. Dudding or to Miss Maynor or to Mr. Mullins or Mr. Lanham and say, you don't have your calculator out. Why don't you have your calculator out? It's an engineering course. It should be like your second language. Mr. Parks has his out. I see that. Do I have a second on that? Okay, good. All right. Remember, the word is engineering. The F stands for fun. Okay. The H stands for happiness. That was a joke, not a very funny one. Okay. I love my job. All right. Now the live load. Okay. Now, okay, so let's consider what's going on with the live load. Okay. So for the live load, we're given 1.6 kips per foot, and we're given a live load, concentrated load, of 25 kips, right? That's what we were given. Okay? So let's see. So here's what I'll do. I'll write that right here. So okay. So let's see if we can reason through what that should look like on the beam. Okay, let's do this. Let's see if we can reason through the load placement. Okay, let's start off with shear. Okay, can somebody tell me where should I put the load to generate the worst case positive shear? I'll give you some letters to go off of. We'll call this A, B, C, we'll call this D, and E. Where should I put the distributed load for worst case positive shear? So we'll call this V max positive. Where should I put the distributed load?
A to B and D to E.
A to B and D to E. What about B to C?
That's what they, A to C, sorry. Put it from A to C? Yeah. That's,
Well, what about right here?
that's only 0.9.
But it's positive. Everywhere that would generate a positive shear is where I'm going to put that load. I propose that I need to put that load right here. That's where I need to put the load. Now, where do I put the point load? To generate the worst case positive shear, where do I put the point load?
A B.
At B. Because B has the worst case positive value. That's where the load goes. Does that make sense? That is the worst case positive shear that I could get. Okay. And how do I compute that? I say that VL positive is 1.6 kips per foot times something plus 25 kips times something. What goes in the 1.6 kips per foot? What do I put right here? 4.9. What do I put? Somebody else. What do I put right here?
0.9.
Hold on. No. Okay. So for the distributed load, I put the areas. For the concentrated load, I put the values. What is the largest positive value on the influence line? 0.4. For the areas, I'm summing these, right? So if you want to be, I guess, maybe a little more specific, we'll say 4 plus 0.9, and here 0.4. If you want, you can put a foot there for the units. And so what is our worst case positive shear?
17.84.
17.84. Do I have a second? Okay. All right. Now, how about the worst case? Oh, yes.
What'd you say for distributed and concentrated, you put in the brackets there.
Okay, let's do that. Let's do that. So let me erase this. So these are areas under the influence line. This is the maximum value on the influence line. It's a good question, okay? Everybody with me on that? Okay, so now let's go back to this beam. The top of this beam is getting erased like crazy. I'm sorry. I'll replace you there. Let's do that. Okay, so there's my section. Tell me where to put the load to generate the worst case negative shear. Well, let's do the distributed load first. But you're right. It'll go right there. Where do I put the distributed load? From C to D. Okay. And then how do I compute it? What do I do? So what goes here?
4.9.
Well, not 4.9.
Negative.
Negative 4.9. What goes here?
Negative 0.7.
Negative 0.7. Exactly right. Okay. And so what do we get for our worst case negative shear?
Negative 25.34.
Negative 25.34. Do I have a second on that?
Yep.
Okay. So this is our answer for our envelope. Does that make sense? So we cannot generate a bigger range of shears with those loads. We can't do it, okay? So we have a dead load shear value, but like we're talking about shears, the dead load shear ended up being 0. So this is the range that we would design for. Now, what I'll tell you is when you all take steel design, we're going to take these values and apply load factors to them and other resistance factoring, all that stuff. We're going to get into design land. But in a nutshell, this is how we're going to do it, okay? Yes?
Do you leave the 25 positive, right? Or do you?
Oh, no, I'm sorry. Yeah, that is negative. Yeah, that's negative. You're right. You're 100% right. Let me rewrite that. That's actually a very important point because there are some instances with like moments where the positive moment will be a value and the negative moment will be 0. So for example, if you have a simply supported beam and you're trying to find a moment envelope right here, the moment envelope that's negative will always be 0 because there's no way that you can place a downward load on the beam right anywhere on the beam and cause this to frown. It will always smile at you. Remember smiley face or frowny face, or remember smiley face positive, frowny face negative, right? You cannot place a vertical load on a beam and make it frown like this. It won't work, right? So that's why this will always be 0. So I'm glad you pointed that out because you're right. That should be negative. Sound good? Okay. So now let's do moment. Okay. So now what we're going to do is let me erase this load again. Okay. And let's do worst case positive live load. Okay. Where do I put the load to generate the worst case response? Remember, this is A, B, C, D, and E. We're using that. So where do I place the load to generate the worst case positive response? Let's start with the distributed load. Where do I put it? From C to E. I put it right here. And that kind of makes sense. I mean, keep in mind, that's our point of interest right here. And placing the load right here would cause it to smile, right? Cause the beam to smile. Where do I put the point load? D, right? I mean, does that load placement kind of make sense if you want to make, I mean, keep in mind, that is your focus. We're focused on that point right here. If you want to make this point smile, put all the load right there. Does that make sense? It should, you know. So what do? We take we do this, okay? What's the value right here for the distributed load? The area under the influence line. What area do we use? Say it again. 42. And again, if you want a unit, it's foot squared, but it doesn't really matter because everything's consistent. And the 25 kips, what was the unit there? Or what was the value there? 4.2. And what is ML positive going to be?
172.2.
Say it again.
172.2.
Second. Okay. Now, what about ML negative? Where do I place the load? Bless you. Where do I place the load if I want the worst case negative response? So let's erase all this. So somebody tell me. Let's see. So where do I place the load if I want the worst case negative response?
A to C.
A to C. And where do I place the point load?
B.
At B, at the hinge. And think about what that does to this point. Remember, that's our point of interest. What's the beam going to do? Well, here it's going to smile, but there it's going to frown, right? That's going to generate the worst case frowny face at our point in question. Make sense? Okay, so 1.6 kip per foot times something plus 25 kips times something. Okay, and 1.6 kips per foot times, what is the value here for the distributed load?
24.
Negative 24. And this one right here?
Negative 24.
There we go. Negative 98.4. Do I have a second on that?
Yeah.
So, okay. I'll give you a sneak peek of what this looks like in the real world, and I'll talk about this on Monday, but I do want to give you a sneak peek so you can at least kind of paint a visceral picture for Monday. Does anybody have any questions on this? Hopefully this is pretty straightforward. Let me kind of show you what this looks like in the real world. How many of you all have heard of AASHTO? Okay, has anybody not heard of AASHTO? If you haven't, AASHTO is the American Association of State Highway and Transportation Officials, and they are one of the main associations that develop a lot of the standards for roads and bridges in the United States. Okay, so there's a AASHTO bridge design specification, an AASHTO specification on the geometric design of highways. How many of you who've taken transportation have heard of the Green Book? AASHTO. Okay, so AASHTO has a particular live load model, and we'll talk about this in more detail on Monday, but this is kind of what it looks like. There's a particular truck that we use to perform analyses and designs of bridges, and so this is what it looks like. What I'm going to do on Monday is I'm going to show you how to use that on a representative problem. But what I kind of want to show you is what a envelope looks like for a bridge. So what we would do, so see this problem right here? This whole problem that we just did, this whole example problem, was focused on that point right there. Just that point, okay? So we would repeat that problem for a different point. Like we did it right here, we would do it right here, do it right here, do it right here, do it right here. How many points do we do? We typically use 10th points. So what we would do is for an 80-foot bridge, we would do one of these analyses at every 8 foot. And at every 8-foot increment, we would have a worst case positive and negative shear, a worst case positive and negative moment, a worst case positive and negative shear for each of these different load components. And so you can then graph it. So like this is what a shear envelope might look like, this is what a moment envelope might look like. And so what you would do is if you were designing a bridge, you would design it such that it can withstand that range of shears and moments. Okay? I don't want to steal Monday's thunder too much because there's a lot of details in here that I'm kind of skipping, and I want to take our time on Monday and discuss that. But what we're going to do on Monday is learn what the actual AASHTO load model is, why it is the way it is, and then how to actually apply it. And so I want to wait to have that real discussion until you do this next homework assignment. So with that, I'm going to keep my promise and actually let you out 3 minutes early. I'm going to pull the code out in case anybody missed it, but I will see you all on Monday.